Hi, research methods students. I'm Dr. Beth Cooper, and this is probably the first video you're watching for the online class or another class. So I'm going to be talking over PowerPoint slides for a little bit. I plan not to do that too much for the class, but I just wanted to throw some words up there this time to make sure you could follow what I was doing. What I want to talk about today is ways of knowing. And the question really is, how do you know stuff? Like, how do you believe things to be true? Where did your information come from? How did you know to watch this video today? Well, was it on Blackboard as an assignment? Did you get an email from me? Somewhere there was information I put down, right? And you believed me when I said, you gotta watch this video. You did. And so I was some sort of authority. I know something you don't, perhaps, about this class, and so you're just doing what I asked. So you know that through authority. After this, you may say next week, oh, I have to watch a video, I'm sure, because we had one last week, I'm sure we'll have one this week. So that would be something you know from experience. How do you know that the world is round? Did a teacher tell you? Did you read it in a book? That would be authority. Are you someone who was on a plane and kind of noticed somehow the curvature of the earth? A student actually said that to me once. I don't know if they can do that, but that would be based on experience. So let's look at a few of these ways of knowing, because there are lots of ways that we get information, and there's lots of ways that we come to believe something is true. And science is just one of those ways. Now, it is the way that this entire course is based on, and it's the only way we're going to talk about pretty much for the rest of the semester. But I wanted to just put it in context. So let me put up real quick some things for you to look at. Okay. Now, different books do it different ways. I've had textbooks that say there's 7 ways of knowing or 5 ways of knowing. By the way, you can always see me over here in the corner if you get bored of the slides. Your book really kind of just uses 3 plus science. So we'll just go with the Morling book and how she characterizes it. So 1 would be experience. Seeing is believing, right? You know something's true because you saw it. All right? That usually is a pretty good way. Now, remember, seeing is believing unless you were mistaken. You can have 4 different witnesses to a car accident and get 4 completely different stories. Okay, we do know that our senses can be tricked. Our brains can organize information incorrectly. When somebody pulls something black out of their jacket and police think it's a gun, but it turns out to be a wallet, we know we can get wrong information from our experience. So we have to be careful because, of course, basing information and beliefs on our experience, often it'll work, but sometimes we can be wrong in the information or the beliefs we have. Now, another way we come to know things to be true is just through thinking. So your book will call this intuition. This could also, intuition might be a gut feeling, but she means that your author as thinking, logic, when we just go, oh, if this is true and that's true, well, I suppose this must be true too. We do that a lot. We do it in science. It's a piece of science, as is experience. We come to believe things based on our logic. Now, we could be wrong. We make errors in our thinking all the time. So we have to be careful about that. Authority. We use this a lot. Somebody that we think knows better than us tells us something. Like, who are authority figures in your life? Parents, teachers, older siblings, people with degrees, Dr. Oz. There's a good example. Sometimes authority figures are wrong, so we have to be careful about the information. But it's a quick, easy way for us to learn stuff and to come to believe things are true. Now, all of these 3, of course, have their downsides. They can all produce wrong information. Authority figures may have a certain agenda, or they may just believe something to be true and they don't have all the facts, and so they're passing on misinformation. That can always happen, but these are things we use every day to come to believe something to be true. Now, science is just another pathway to belief, understanding, or hopefully truth. It's another way that we generate knowledge and we generate information and things that we believe to be true. Now, can science be wrong? Absolutely. Things, results come out, and a year or two down the road, we go, oh, wait, we were wrong about that. Or it only worked in those very certain conditions, or it's what we would call type 1 error. We thought it was true, now it's not true. Science can be wrong. Now, I like science personally because it does have something built into it that none of the other ways of knowing have, and that's a method of self-correction. So science can certainly produce wrong information, and it does occasionally, but we have things called peer review, where people critique each other's work, usually on the way to getting it published. We have things like replication. So if we don't do an experiment one time and say, that's it, we know, now we're done. People redo it, and they may redo it with changing little things to kind of test it out. But if it doesn't hold up over and over, we figure out, oh, wait a minute, we might have been wrong. We have to change our ideas. So it's a really great method. It takes a lot more work and more time than maybe these other methods. And there's certain questions that science can't even answer because they're qualities a question has to have before science can even touch it. And we'll get to that. All right. Now, here's an example of how science can be wrong, or, well, how we can misuse it. If you see a commercial with a guy in a white lab coat, I go, oh, 3 out of 4 dentists say you should chew this gum. Okay, just because he looks sciencey, or, even if he is a scientist and we hear him say something, we go, oh, well, it must be true then because you're a scientist. Well, that's just the method of authority. That's no better. If we're going to be using scientific method as a way for us, like me, who I'm not out collecting data every day, I'm not out running experiments, but I still like science. The way I use it as a consumer is I may see an article about a scientific study, and I'm not just going to take what the article says. I hope you looked at that pretty funny cartoon in your textbook about how scientific things go through journalists and they get to your grandmother and then it's all something different. But I'm going to just be skeptical. I'm going to be a skeptical consumer. I'm going to ask, well, how did they get the people in their study? How did they do their sampling? What was their sample size? How did they define their variables? How did they measure their dependent variable? Okay, how did they manipulate their groups? Did they use random assignment? Are they making just a correlational or association claim? Or was this an actual experiment with random assignment and they're making a causal claim? I need to ask all these questions for me to use science as a way to come to believe things. I want to know how data were collected. I don't just read a headline and go, oh, scientists say, must be true. That, of course, is simply authority. All right, so here's what science has. It's self-correcting. Big ones are peer review, replication. Because one thing in science that you have to do that the other ways of knowing don't do is you have to be very transparent. You have to tell people how you collected your data, how you measured it, all the steps you went through. You have to give them your data, show your data in graph form maybe. Often it is in, sort of averages and things. You're not giving every little raw data piece, but you're giving descriptive statistics that describe your data set. And all of that is in your paper so people can see it and then they can decide if they agree with your conclusions or not. But it's very transparent and it's out there. The other ways don't have to do that. It's just, oh, take my word for it. I was there, I saw it, this is what happened. There's no more advice I can, information I can give you. That was what I observed. So if you believe that person, you're you don't have a way of correcting that. You either believe them or you don't. All right, so science has that pretty cool thing built into it that the others don't. That's certainly one reason I like it, and I think that's why it's very popular as a way of knowing in our society. Let's see. Now, your book talks about the data theory cycle, and that's a great image. I want you to kind of look at that. I'm just going to put a few more steps in. It's not different, but there is a certain path, a method that people go through. Now, they may enter the path at different places or be thinking about different parts of the process. Even when they're down here, they're thinking up here. But there are some steps to the scientific method that I think it's worth knowing. And again, different books might have this a little differently, but it's okay. Everyone's talking about the same thing. Okay, so first of all, we have some kind of idea, some theory of how something works, right? And so from that theory, and these theories, by the way, are based on what everyone else has done before. So we go out, we see what other people have done. And then we go, okay, so this is what we know now, right? This is sort of how all the pieces fit together. And that's our scientific theory. Now, from that theory, the way we understand how we think things work now on a particular topic, we're going to then come up with a hypothesis, one specific prediction that we can then go test. Now, you may have often heard hypotheses described as an educated guess. I hate that word. I hate that. It's not a guess. There's no guesswork involved at all. It's based on the theory. If this is how things work, then if we do this, then we will expect, if X, then Z, or something. Okay, so there's very particular reasons, and it's not just like, oh, I don't know, maybe it's this, just my hypothesis. No. This is a scientific hypothesis. It's different. All right, specific and based on a theory. Now, once we have a hypothesis we want to test, we have to go ahead and design the study. Now, this step, design the study, is really the bulk of this class. 295 is going to be about, or 395 if you're watching, it's going to be about that design. That's where the experimenter does a lot of work and has to be very creative and very careful, okay? Because your data are only as good as your design, right? And we're trying to draw good conclusions and see if our hypothesis is supported or not, see if we're right or not. And so it has to be a great design. So a lot of what we do in this class really is just around this particular step of design. How do you design a good study to answer your question? All right, so then we actually have to collect the data, and researchers don't do that. They have undergraduates working in their lab that actually do the grunt work, collect the data, typically graduate students. Once you have the data, then you have to do your statistics. For most studies, there are certain study designs that have no statistics, which is pretty fun. But you, at some point, will probably have to take a statistics course. And there's a good reason for it, because we get all these numbers, and then what do we do with them? So we run our stats to see if there's something interesting going on. And then we have to communicate what we found. Now, typically, you're going to start doing this by maybe taking your results to a scientific meeting. That typically researchers will go one or two meetings a year. Every year they'll go. And they may have a poster presentation. They may give a short, like 15-minute oral presentation. And typically they do that on the way to publishing the results in a journal. And of course, the publication process has a lot of peer review. The editors send it out to people to look through it, comb through it, kind of pick it apart. Now, we're not done. Once we get it out there, you start over, because your results will either support your theory or they won't support the theory. And if you have enough results where it's not working the way we thought it was, you actually have to change your theory. That's a pretty interesting part of science. So, that's why the theory data cycle in your book, I love how she has a couple of steps and then she's got these arrows that go back up the top. So on here on my slide, I wish I had these arrows that would go back up. And either you support the theory and you're feeling real better about it and your confidence in the theory is building, or it's not working out and you have to adjust it or change it or do something, because we think there's this reality out there. We think there's this actual answer to our question, and we want to figure out what it is. So we're willing to change our explanation when we get new data that doesn't fit the old explanation. You change the explanation to fit the data. The data are what they are, and then we're trying to put them together into a good explanation. So there's some things about science that other ways of knowing don't have. They may have pieces of it. So when we're doing science, we have observations, which is experience. We see things. But what's important is they're systematic. I may think something's true because I've observed it once. What if I don't know, it's Greek rush and people are going to come sign up for my sorority, and I meet these ladies, and one of them I meet, and she's a real bitch, and I think, like, man, I don't like her. She's terrible. Right. Well, that was one meeting, right? There are explanations for maybe why that person was not in a good mood that day, or why she was rude. You know, maybe she's a horrible person, or maybe something really terrible just happened, or, you know, there could be other things. And that's why we do systematic observations, because one or two observations here or there could be reasons that we're not aware of that are driving what we see. When we're systematic about it, we want to make sure we have a good enough number of observations that we think that we're seeing valid representation of somebody's behavior, perhaps, and we're very careful about it. We're trying to rule out other factors that we might not be aware of. So we're very systematic about it. And we're not so systematic in our own life. When we see something, we're going, huh, and we draw conclusions about people or things, and just from a little bit of observation. Okay. And similarly, we're only going to draw conclusions based on data, not just how we feel or think it must be true. It's got to have data backing it up. As I said, we have to tell everybody, how did you collect your data and what were the results? And in the discussion of a paper, I can do a little speculation, I can draw some inferences, but the reader of my paper gets to see my methods and my results, and they can decide, do they agree with my interpretation of these results or not? And they can do that because I have to tell them how I collected everything. Now, conclusions are always tentative. You know, every paper is going to have, well, you know, these were the people in my study, this is how I measured it, and if you change something, maybe the results would be a little bit different. We always know there's a possibility that it's either just for this situation, or what's kind of more important is the statistics that we use largely are based on probabilities. And we say things are true, or we say groups are significantly different, always knowing that there's just a little probability that the data we collected makes it look different between our groups, when really it's just kind of a fluke and noise in the data, and it just kind of came out that way. So scientists that use probability statistics, which is, you know, a lot of people, and a lot of people in psychology, when they're using statistics, they know, well, the statistics tell you what's the likelihood of this happening. There's a 95% chance that your sample contains the real data of this population you're interested in. I know that doesn't mean a lot right now, but we know there's always a little bit of a chance that what our data show us are not exactly what we want it to be. So scientists are always a little bit tentative. Okay, science can only ask questions about things where it's possible to collect the data. There are questions that we want answers to that science cannot answer. So, for example, if you were to ask me, oh, Dr. Cooper, what should I be when I grow up so I can be happy? And I can say, well, you know, what do you like to do? And oh, well, people that like those things often report they're happy in these sorts of jobs. Or, you know, but to be honest, I can't tell you exactly for you what job is the best. I can answer questions on, all right, psych majors that go on to these careers report this amount of happiness, report they make enough income to pay their bills, or they, you know, there are things I can collect data on, but some things I can't say, oh, this is it for you. Is there a God? That's an easy one. Maybe not easy, but that's a question science can't answer. There is no data we could collect that could say yes or no, right? Because if somebody wants to believe, they can always come up with an answer for something. There's just no way to rule out certain things. So that is also a limit of science. So it's related to this last one. Science can only deal with theories that are falsifiable. That's a word you'll see. All it means is it's possible to test them. Okay, there's no way to come up with a definitive test about is there a God or not. Okay. If Freudian theory is often used as an example for this too. You know, if he has some kind of dream analysis. Now, people have tested Freudian dream theory, and Aaron Beck in particular with cognitive therapy had a testable hypothesis that was collecting data, and found that Freudian dream theory wasn't holding up. But Freud himself, when he was working on the dream analysis, was kind of, it became characterized as, well, if you dreamt about sawing wood, it meant this. Well, how do you know? How do you know it means that? I mean, if there's always, and if you didn't mean that, it's because you're just repressing your memories, and there's just no way for some ideas to show that it can be wrong. And if that's true, then it doesn't fall under the realm of science. There has to be a way to say, this is right or this is wrong. And if you can't, it may still be very important and interesting, but science isn't going to be able to help you on that specific question. Now, we can always find related questions. If you came up to me at the end of the semester, oh, my boyfriend proposed to me, should I say yes? I don't know, but I can give you data on, let's see, divorce rates for people who get married right out of college or at certain ages, or I could give you personality profiles and see, what's the probability based on your match. That we could collect certain data, but that particular question, is this the right person for me? Science can't help you there. Now, let's see. I do want to say something about scientific theories. Be absolutely clear, scientific theories are not just a theory. They're special. This is my short definition. Scientific theory is the best explanation for what we know now. Now, I want to unpack that a little bit. What we know now is all the data that has already been collected on some question, right? A scientific theory has to take all of that, not just some of it, not just the pieces I like and ignore the rest. Everything that we think was well collected, a good study, and take all these things we know and find a story, make up a story that fits these pieces together in the most coherent way. Now, there could be holes in the story, okay, and things that need to be, data that need to be collected and put together. So one analogy is to think of the scientific theory as the house, and individual facts or things that come out from individual studies, those are the bricks, okay? We're trying to put them together into this explanation. If we have this story and there's a hole there, we can go, well, if this story works the way I think it does, then that hole, if we look at this, this is what we should find, because that's what should fit there. Then we design a study, we go out and find it if it holds up. If it doesn't, we got to redesign our house to get rid of that funny hole because it apparently doesn't fit. All right, this is already said on the last slide. Scientific theories have to generate hypotheses that you can test, meaning there's some possible way to collect data to test them. Otherwise, it's not scientific. All right, now good theories in science are going to help us organize everything we know, take all these individual studies and put them together in some nice coherent package. And from that, then they're going to suggest new predictions, new hypotheses that we can test. So they're generative. And to do this, there's this word parsimony that is important in science. We say they're parsimonious. So I could take a number of studies, building blocks, and I can put them together in different ways, right? But to be scientific, I want to put it together in the most clean, I don't want to say simple, but you will hear this, simple way, but really parsimonious way. So scientific theories, it's not that they're simple. I mean, some of them are very complicated, but replace the idea of simple with parsimonious. And what that means is they're the least number of unknowns in your theory, in your story. They're the least number of assumptions or leaps of faith. So here's my example. Let's say you come home to your apartment at the end of the day, and there's a note on the sink that says, "Clean up your dishes, you lousy slob." And you're thinking, okay, well, there's a couple of hypotheses to who left me this note, right? It could have been, well, it could have been my roommate. She was here when I left. She's been complaining recently about my dirty dishes. She knows how to write. She has pen, paper. Could have been her. It's one hypothesis. The other hypothesis is it could have been my dog Skippy. Skippy too was here when I left today. Had all day to do this. That's pretty much all I know. So there are a few holes in this theory. Skippy has to write in cursive with his little paws. He had to be able to get pen and paper. He had to even care about my dirty dishes. You think that might even benefit him? He could eat stuff off them. So while the Skippy hypothesis, proved to me I'm wrong, right? I suppose that's one hypothesis, and the roommate is a competing hypothesis. But the Skippy has a lot more leaps of faith, a lot more assumptions, things that would have to be true for it to be true. So I'm pretty much going to ignore that one and go with the more parsimonious explanation. I still don't know if my roommate did it, but it's more parsimonious to assume that she did. All right, we'll put our screen share just back up to see what we have left here coming into the home stretch. Come on. Okay, so some limits on science. Of course, we can only study what we can measure. Think about things that we didn't know before: microscopes, MRI machines. Technology helps us measure a lot, so that's going to be important. Again, I mentioned some things that it's impossible to collect data on. Is there a God? Who should you marry? We're limited by our own imaginations. If you think about it, we are brains studying brains, which is kind of strange. There's got to be some kind of limit there. And of course, there are things we might be curious about, but you would never collect that data because it would be completely unethical. So that certainly limits. All right. I do want to mention a little bit about pseudoscience. These are things that dress them up as science. They may look sciencey, but they're fundamental differences. Now, here's probably the biggest one. In science, as I said, we make the theory fit the data. So if I run an experiment and I do a good experiment and I do it a couple times and it's just coming out a different way and it doesn't match my theory, I have to change my theory. Pseudoscience does it differently. In pseudoscience, they have an idea that they want to keep. And they go out and find the data that fits. And if there's data that doesn't fit, well, let's just find, there's got to be a problem with that data. Let's find out what's wrong with it. Or let's ignore it. Or So, all right, the easiest example for this, and it just works so well as an example, is creationist science. Okay, I went to a creationist museum outside of San Diego one time and took the tour, and then was talking to the tour guide afterwards, and it was a great conversation because I had this thing in mind, like science is you have the theory, and if the data are what they are, man, and if it contradicts your theory, you got to change your theory. And so I say to the guy, like, scientists are willing to change their theory in light of new data, but you won't. And this is perfect. He goes, well, of course they won't. We're both looking for the truth, right? I said, yeah. He goes, I know the truth. God revealed it to me in the Bible. I thought, that is a perfect answer, right? And it demonstrates how different science is from what he was doing, okay? He had the story that he believed to be true. Now, what way of knowing did he use? Authority, okay? And his authority is probably the church he was raised in the book that church he uses, and his parents and his teachers and ministers. And all right, so here's this person that believes this story. And then he's going to go find evidence that supports that story. That's fine. That's great. Have at it. Have a great life. Have a great museum, right? But it's not science, because that's not how science works. Science is you find the data, you go out and measure things, and then you go, so if all these things are true, because we're really careful, and if we screwed up, we have ways to figure that out. We'll figure it out eventually, and then we'll figure out, okay, this is the real data. Then the story emerges from that. You don't start with it and then pick this and, well, you got to be wrong and you don't really have a PhD. And it's just different, completely different. And so what that's not too hard to understand. I guess what the real difficulty is when usually in selling products, they're going to dress themselves up in look sciencey. Okay, and so as consumers, we have to be very skeptical about people's claims because we do feel like, oh, science has this weight or something, and if it's done well, it does. It can produce really great information, but we have to be skeptical because people can be selling us things or selling us ideas that are scientific, and they're not, because they're not following the rules. There are certain rules to this. All right, so let me see what's left. You really are close, I promise. Okay, science is progressive. You're always building on what came before. That's why you got to read a lot of journal articles when you're in graduate school, so you can figure out what you're going to do next. So new questions come up from what's been done before. And completely new areas, of course, get started in science by things we just don't know yet. But any study is going to produce new questions. And sometimes people, in the general population may think that's frustrating, like you never get to the end. Well, that's how science works. There is no end. We can't know everything. So every study is going to go, well, I wonder, what if we did this? Or would it work on somebody else? Or is it, it's true in 10-year-olds? Is it true in 50-year-olds? What about this culture? And then, of course, everything changes. Is it still true? Do we still think this way? It makes it fun. There's just so much to know. Okay, so goals of science are to describe, predict, and control. And this is great. This would be great. I mean, what if we could describe, what if we're interested in depression? Well, what are we talking about? What does it look like? How would you know if somebody has it? Okay, that would be the describe sort of portion. And then predict it. Well, what are some things that might lead to it? What are some things associated with depression? And of course, we want to know that because ultimately control it. How can we prevent somebody from having to deal with this? Or how can we treat somebody who's dealing with it? We absolutely want to control. We want to help make people happy and make good choices and, be healthy and keep the planet healthy. This is an excellent goal, is to be able to help us control the decisions we make and the things that we do. Now, your book is going to use a great method of kind of getting you used to the different types of research that map onto this. When we're in the describing phase, you're going to see what's often called frequency claims. They may come from descriptive studies, and this is just when we're kind of saying, well, here's what's out there. Like, so let's say we're interested, we work at UT, and we know that not everybody who starts as a freshman graduates. And so we want to increase the number of students who stay and finish their degree. We hate to think people go off with student debt and they didn't finish their degrees, so they won't get the benefit. How do we keep people engaged? And so we might want to know, well, how many students drop out when they're before the end of freshman year? Or when do they drop out? Okay, who are these people we're talking about? What kind of classes did they take? What kind of majors did they have? Where did they come from? And then we're going to quickly kind of move into association claims. Is there any connections? Like, are people more likely to drop out if they lived off campus compared to on campus? Maybe people live on campus and then they feel connected and they stay. Are you more or less likely to be successful if you've had certain courses in high school? If you have a certain reading level or math level? And you can see, are there connections? Are there correlations between this? What if you're first generation college student? What if you're, traveled a long way to get here? Anything. We want to see if there's a connection. So what we really want to get to is control. How can we help people be successful so they don't transfer, they don't drop out? Figuring out what can we do. And then we have to go and try it. And we actually run an experiment. What if we offered first generation college students an extra 1 credit class freshman year to help them transition and be successful? Or what if we have somebody who's has a low GPA from high school for various reasons, and we can do things to help them, bridge that, get up to the college speed and be successful? Should we require freshmen to live on campus because that alone is enough to make them more connected and not drop out, not transfer? So the control stage is definitely a goal of science. All right. I know I've been talking a long time. I'm sorry. At least you could pause and get a snack or go to the bathroom, unlike in class. So, but hopefully this will just get us started with some videos. There are going to be a few a week, and I got to really keep up with this stuff. Hopefully, you know, look at chapter 1 and chapter 2 in the Morling book, and there are certainly some assignments posted for you to do on this. So we'll see you later.